everybody, and welcome to our webcast on exploring PAM4 short-reach data center interconnects. This is the 7th in a series of webcasts sponsored by DuPont Silicon Valley Technology Center and the Consortium for Onboard Optics, or COBO. So over the next hour, we'll be discussing PAM4 AOC, active optical cables, and SR modules, short-reach modules, using analog CDR technology. So as compared to DSP approaches, there's the prospect of lower power consumption, reduced latency, easier manufacturability, and perhaps lower pricing in volume for this technology. But questions remain about interoperability, reach, and even scaling. Will we get to 800 gig and up? So we're fortunate today to have two of the leading companies in this space with us. Our first guest, Kees Propstra, is Vice President of Marketing at MultiLane, which is a leading provider of high-speed optical, I/O, and data center interconnect test solutions. We'll also hear from Dr. Yong-san, who's CTO and Chief Marketing Officer at Optomind, which offers an advanced optical engine technology for enabling 400 gig QSFP 56DD AOC and SR8 optical transceivers using analog CDR technology. So during this webcast, the audience members will be in listen-only mode, but we welcome your questions. Please use the Zoom Q&A function at the bottom instead of the chat option. Just type in your questions as we go along, and if you could please indicate who the question is addressed to, Kees or Yong-san, that would be great. This webinar should last about 45 minutes and giving us about 15 minutes for the Q&A portion. So with that, I'll also mention that there's an archive of this webcast that we'll post online along with all of the slides. And with that, let's kick it off. So Kees, welcome to the webcast.
So first of all, I would like to thank COBO. First of all, thanks Jim for the introduction. And I would like to thank COBO for inviting me to speak at this webcast. I just learned it's not webinar; it's called Webcast. It's truly an honor to be part of this. So this week is a very busy week for our profession because we have ECOG going on in Europe right now, and CIOE is going to start tomorrow. So it's a privilege to have you guys on the call and listen to our conversation. So my focus will be really, I'll give an update on the status of the data center interconnect industry, what are some of the emerging trends, and then also let's talk about some of the test strategies that will enable the evolution of the technologies. So let's have a look at where we are today. So the state-of-the-art technology is really, we have the 50G ports, the SerDes, we have the 400G interconnect ports in the systems, and typically the switches that we're using in the data centers are 12.8 or 25.6 T. And if you look at the graph on the left, the light counting graph, you can see that 400G Ethernet really started to become big in 2020, and we're expecting very aggressive growth over the next 5 to 10 years. It's going to probably take over 100G Ethernet as the dominant port speed in this industry. But what you can also see that there's, of course, is the next generation is already around the corner. So 800G, is really in an early stage. It's going to be 100G per channel, which makes it, kind of challenging. It's going to be 800G per port, per interconnect, and then it's typically being used in conjunction with 50 terabits per second switches. So obviously that has a little impact on the test procedure. So if you look at the typical technology adoption curve, so 100G is really past its peak. It's probably still the most dominant port speed. 400G is the new technology upcoming, so it's really ramping quickly, and it means that you're going to be in mass deployment mode. So you have, that really impacts your test requirements. So first of all, you probably need to have, manufacturing test capabilities to test the interconnects. You need to be able to test your systems before they go into full deployment in the field. And then also with all these interconnects and pluggables in the field, there's going to be situations where you have a suspicious interconnect and you need to know whether the interconnect is still working, whether you need to send it back to your supplier or not. So you need to have automate testers, kind of easy to use automate testers to support that part of the ecosystem. And then of course, 800G, I think we can honestly say that we have passed the chasm, the point of no return. A lot of people working on it. It seems to really, be kicking off with lots of development activities, and you need to have the tools to enable that development phase. So obviously, having the fixtures to be able to, to drive your interconnects, to test your ports is critical. Having the loopbacks to do the system testing, but also very important, you need to have the 800G birds to drive the interconnects or to test the 800G ports. So obviously, it's very important that you plan your test strategy to reduce the risks and and speed up your time to market. So this is kind of a novel concept, this idea of automated testers for pluggables. And the pain point that it addresses is really, you have like hundreds of thousands, probably even millions of these pluggables, whether it's DAC cables or transceivers in the field. They're being used. Sometimes, obviously, they're suspicious. You don't know whether they're working. You need to have, an independent referee to say, yes, it's working fine or not. But so that it means that you need to have an easy way to test it, but it needs to be a very complete test. So that's kind of a contradiction. So what we did is we developed an automated tester. You just plug in the pluggable, the transceiver, or the DAC cable, and then you get a full test report without any human intervention. So it's very easy to use, but you get like a high-end test report. In case of transceivers, you get a full optical test report. You get a receiver sensitivity curve to understand whether that device is working properly or not. So this is very important to support the 400G mass deployment phase. So another trend that we're seeing, and this is really, in addition to the short reads that Young Sung is going to talk about. So obviously for the shorter distances, typically the copper cable is still the dominant interconnect. It's the cheapest, lowest power, but at 50G, especially at 100G, the reaches are going to be limited. So you need to have an active copper cable to extend the reach. As you can see on the plot on the right that was provided by Spectral 7. So what we're seeing in the industry, there's really two different approaches. You have the redriver approach, where you basically clean up the signal with some equalization and gain, which you can see on the left, the eye diagram on the left. Or you have retimer-based solutions, where you basically recover the signal and send out a clean copy of that signal, and you get a kind of a more open eye. Obviously, that will impact, the testing strategy that you will need to apply to be able to understand whether the device is working properly. And we see some activities from the HiWi consortium to really push the active electrical cables into the market. So on one side, we have the retimer-based solution, so kind of the clean eye. It's kind of a plug-and-play solution, meaning you get the cable, you plug it into the system, it works, you have a standard interface. So obviously, your test solution should represent that. So we are developing right now a solution in conjunction with HiWire, where you basically plug in the cable, you do a seamless validation, you do a link-up time, how long does it take for your cable to be ready, and then you do a figure of merit test, which is based, in this case, on pre and post-fac BER. So very easy to use to be able to get a test report like that. So then on the other side, we have active copper cables, the redriver based, where you basically clean up the signal with gain and equalization. And that's a more intricate balance between the IC settings in the active cable, the transmitter equalization on the host and the receiver on the host. So you need to have a lot of insight into behavior to be able to optimize that. So we have a parametric cable test solution where a bird, drives the signal into the active copper cable, and then you have an oscilloscope to characterize the signal, and that will give you S parameter characterization, I diagram characterization, so that you can optimize the settings to get to this optimum condition for the cable. And you can see that both approaches have a place in the market. They have a specific niche to optimize the reach, cost, and power. Sorry. Another trend that we're seeing is the OpenEye consortium. So what they're trying to do is they're trying to support bandwidth growth while reducing cost and power per gigabit. Obviously, power consumption and cost is really critical. The optical interconnect plays a dominant role in the data center, but also impacts the cost and power consumption significantly. So anything that can optimize that is critical. So, the premise of OpenEye MSA is that, like, hey, if you have this expensive DSP technology, that is really, it's a huge investment. Even if you amortize that over a large volume of interconnects, it's still a pretty dominant cost. Analog technology is significantly less expensive. If you look at the power consumption from 100G going to 400G, you can have a significant improvement in power. And then if you go from digital to analog, we believe, or OpenEye believes that you can achieve another 20% of power reduction, which is very significant. And then with regards to latency, obviously, if you have a DSP-based interconnect, you will have some overhead that will add some delay, some latency. So that could be up to almost 50% of the latency in your system, as opposed to if you have a more analog approach where it may be less than 10%. So, very important development, but of course that will impact, how you look at the optics and how you can develop it. So the optical testing, just the transmitter characterization. One of the things of OpenEye is they want to, optimize the test procedure, make it as easy as possible. We have TDQ in IEEE specifications. It works, but it's complicated. So with analog technology, you can basically go back to an eye diagram. So a very simple measurement would be a bird driving your DOT through an MCB module compliance board, and then characterize the optical signal on an optical oscilloscope. So we developed an OpenEye MSA personality on the oscilloscope so that you get all the measurements. That's very, very easy, very intuitive. The question now, of course, does it do what it is supposed to do? So the next slide, and honestly, OpenEye is conducting a pretty large interop study that's going on as we speak, where we test a lot of devices, make sure they interoperate. We'll do the characterization through transmitter measurements, BER measurements. Those results will be published later this year. But just a quick, a synopsis of that. We did some experiments in the lab where you see eye diagrams on the top measured by an oscilloscope. And then we also have a setup, you can see that at the bottom, where a bird drives the signal into the optics, the SR optics. And then we have a 100-meter cable to loop the signal back to the optics to do a BR measurement. So on the left, you can see, a very clean eye, mask hit ratio of like 5 in a million, and then a very clean BR. And think about it, this is like, there's no DSP involved here, there's no equalization. This is the raw signal captured, in the bird, but also on the oscilloscope. And the BER is 1 E minus 11. Then on the right, you have a cleaner eye diagram. You can see the mask hit ratio is almost 10 times better, and also the BER is like significantly better, and it's like 2 E minus 12. So there's a good correlation. Of course, this is very limited data, and we need to have more of these results. But the concept here is like, hey, the eye diagram, it looks really good. It's very clean. You get an astonishingly good BER without any equalization. You know, this is a kind of a very intuitive concept, and we can probably start using this for OpenEye. So another phase, of course, we already kind of alluded to is 800G with 112G per channel. You know, that's a different beast. PAM4 is difficult, and now we're going to do this at 50 gigabaud, 112 gigabits per second. So some of the things that you see, so first of all, you know, the signal is intrinsically, you know, dirty. It looks like noise. So you need to have very advanced equalization to open up the eye, to clean up the signal and recover the bits properly. Going from 26 gigabaud to 53 gigabaud, obviously now the Nyquist frequency is at 26 gigahertz. You know, your compliance masks are going to be really tough to meet. You know, all of a sudden now you need to have the comparable specs at 26 gigahertz versus 13 gigahertz. That is not so easy. Fabrication tolerance are going to play a more dominant role. So something that was working at 50 gigabits per second may not be working at 100 gigabits per second. So you really need to make sure that you work closely with your you know, supplier, you know, validate the fabrication tolerances and probably tighten them up to be able to really get the desired results. And last but not least, obviously to develop these kind of products, to do the complex routing, you need to have a couple of tools in your design team, some advanced tools to really get to these optimum designs. And the specifications that we're tracking, of course, are IEEE, CK, and OIF, the CEI 112G. But you know, it's going to be hard. It's a next technology evolution. So you really need to make sure that you have a good design procedure that includes a rigorous test procedure or you know, a test strategy to be able to get all the information to figure out how you can optimize your designs in as short a time as possible. So on one side, of course, you have the interconnect. The interconnect needs to be tested. Is it meeting the specifications? Some basic tools that are available for that, of course, are the module compliance board that gives you access to the high-speed signals, gives you access to the CMOS registers, so you can program the pluggable transceiver or DAC or active cable, and then it allows you to test these, you know, typically with a bit error rate tester, because that's closest to how, you know, the pluggable is going to be used in a real system environment. So that's on one side, testing the pluggable. Then a very important thing is interoperability. If you plug in your transceiver or active cable into your system, there needs to be some kind of a handshake to make sure that the device is going to work properly. So that CMOS interaction needs to work fine and needs to be spec compliant. So you need to have some tools to validate that. So we developed an adapter that will give you access to the CMOS, the I2C interface. You can actually plug a CMOS analyzer board on top of that. That comes with a software GUI, so that you really can visualize the I2C interaction. You can validate that you're CMOS compliant. You can also program the host and the transceiver, and you can even look at the command execution through kind of a state machine diagram. So this is really important because, you know, the host can work, the transceiver can work. If they don't interoperate, then we have a problem. So this is an important step that you need to validate. Then, of course, on the other side, you have the host board. You need to make sure that is spec compliant and also robust enough to be able to work with all the conditions that it's going to see. And the first step is you need to have a host compliance board, again, to get access to the high-speed signals. Then you can combine that with a BERT to drive in a clean signal to validate that it is working, but also to drive in a dirty signal, you know, with some jitter tolerance, like sinusoidal jitter, crosstalk noise, minimum amplitude, to see like, hey, are you spec compliant, but also the stressed receiver conditions. So very important. And you have the three elements, the key elements that are working just fine. So then on top of that, you want to do some system stress testing before you send your system into the real world. So you really want to populate your system, fully, and then test it for signal integrity, again, seamless compatibility, but more importantly, the thermal household. If you have a fully populated system running at full speed, you need to make sure that, of course, thermal household is in order and you don't overheat the system. So we developed loopback modules that can be used to emulate the pluggable, the transceiver, or the DAC, and they can be used for system testing, very detailed system testing. And that's a very important step before you deploy, of course, your system into the real world. Another thing that you may want to do, and we developed like a channel board with high loss traces, just to do some additional stress testing on the IC that's being used in the system. Add some channel, see whether your receiver can deal with that, can compensate for these additional losses to make sure that you have sufficient margin. So last but not least, this is probably the most important slide of this 800G section is there's some unique 112G per channel challenges that you need to look at. So first of all, you have a wide range of pluggables that you're going to plug into your system. You need to make sure that your system can handle it. So you need to emulate all those different types of pluggables and test for that. Test again the signal integrity, the seamless, and the thermal household. So we developed loss target loopbacks that emulate passive DACs with certain loss profiles so that you can test them into your system. We developed a 3 dB, 6 dB, and 9 dB loss at Nyquist, which seems to be pretty close to the DACs that are going to be used in these kind of systems. Another thing is you can test it with a low loss loopback and really an optimized path, less than 1 dB, to emulate high reflection pluggables, so that you can also test that in your system environment. But the most important new development for 800G are active loopbacks. You can think about it like every port on your system is going to be slightly different. You have really lossy, worst case lossy ports on one side, and then on the other side, you have very complex pluggables that need a kind of a link optimization that requires equalization inside the pluggable, or also the transmit and receive equalization. So to have an active loopback that can emulate those kind of conditions and test those worst case ports as well as the very complex pluggables, that is going to be very critical for 800G. And this is probably going to be one of the biggest innovations for system testing for 800G are these active loopbacks. And of course, they have some smart electronics inside that you can use for maybe some additional analysis. So this is under development, but this is going to be a very critical element of the 800G testing. So in summary, there's a couple of things that we talked about. So obviously 400G is really shipping in volume today. We're in mass deployment mode that really impacts, the test conditions. So really, you need to be able to do mass production and test in production. You need to be able to do system deployment. So you want to do the system testing with the loopbacks. And then also very important, you have all these interconnects in the field. How can we test them to make sure that if we have a failing device, is it working, is it not working? So have automated RMA testers is really critical for this technology. Then there's a lot of new technologies that are going to be deployed at 400G, but also at 800G to focus on the optimization of cost, power, and reach. That requires new test methodologies. We're all starting to develop them. It looks like we have it under control, but there still need to validate some of these elements. And then, of course, we have 800G around the corner with its unique 112G per channel challenges. And, every technology evolution is hard. This one is no exception. To be able to reduce the risk and to optimize the time to market, you just need to plan very rigorous test strategy. If you get enough information from all these elements that are part of the design, you should be able to handle this and get enough information to make the optimizations that are required before this becomes a commercially viable technology. So this is what I wanted to present today, and I will now hand over to Young Sun from Optomind, and he's going to talk in a lot of detail about very exciting optical short reach PAM4 technology. And with this, Young, it's all yours.
Thank you for attending my presentation at COBO webinar. I appreciate DuPont Silicon Valley Technology Center and COBO organization to be a sponsor and support this webcast. My name is Young Sun, the CTO and CMO at Optomind. I'm thrilled to present our PAM4 SR solutions for huge volume demand in the advanced data center today. Based on famous Cisco research on global cloud index, over 80% of data traffic is generated within data center in North America. Total east-west traffic is over 90%, and it means shorter reach interconnect is driving more data traffic than longer reach. Traditionally, rack local traffic is governed by DAC, copper cable only. As data rate increases beyond 50 Gbps per channel, and 8 channels of form factor such as QSFP-DD becomes popular, cable management and handling within the rack becomes a nightmare very seriously. Thick copper cable is too heavy and rigid to handle and thick to block the airflow seriously. Advanced HPC systems already started adopting AOC for top of rack as well as rack-to-rack interconnect to overcome the cable issue. Light counting presented market for Ethernet and DWDM optics at OIF last February. One interesting slide shows the same as Cisco Cloud Index result. Most data traffic through optical cable is between 100 meter and 2 kilometers. If we narrow down it to high data rate only, like aggregated 100 Gbps and beyond, far more optical bandwidth will be used within shorter than 100 meter. That area becomes a sweet spot of the market with AOC adoption more and more. Another interesting result on total cost of network connectivity from Cisco. As you see, the portion of BOM cost becomes larger for optics as the data rate goes faster. It is natural that reduction of network hardware cost is decreasing much faster than cost of optics. Optics complexity and its nature of signal integrity at higher data rate make it happen, especially at 400G and beyond. Optics technology shall require more cost innovation in volume production to satisfy huge market demand coming this time. In my view, architectural paradigm shift is required for 400G and beyond in data center. Today, switch in data center moves at higher speed from 100G towards 400G. The number of ports in a switch is increased to support more servers to save rack space and future expansion. The location of the switch will be changed from top of rack to mid of row or end of row to make layout of rack more flexible. DAC could not cover mid of row or end of row reach for 400 Gbps data rate. Pixel SR optics and AOC will replace copper DAC over 10 meter with a multimode fiber link. The market requires high volume manufacturing of AOC and SR optics module to meet supply chain management without shortage of the product. Direct driving current modulation of VCSEL with PAM4 signaling is more difficult than electro-absorption type modulation of laser diode to make a good optical signal. DSP is an approach to get better signal performance of PAM4, and it is popular in the market. DSP consumes more power than analog CDR and requires longer latency, which is not desirable for HPC, AI, and machine learning application. Analog CDR is a viable solution in PAM4 SR optics, but it is not popular in the market yet. We should consider complexity of multiple parameters in designing VCSEL-based optical link in PAM4. Multimode high-speed VCSEL has various beam profiles, including beam divergence and spatial mode distribution. Optics design requires to receive all the beams from the VCSEL to transmit high-quality PAM4 signal to receiver. Direct modulation of VCSEL for PAM4 signal requires maintaining linearity for the operating temperature range. PAM4 optical signal performance is influenced by various parameters, including RIN, spatial mode partitioning noise, and optical feedback and crosstalk. We should consider how these parameters could be minimized in optics design. Optomind has a very unique optical engine with its own optics design using individual VCSEL and PD. We achieved outstanding results from the design for the following: negligible optical crosstalk between channels, which can make lower optical noise from neighboring channel. We could optimize optical coupling for all channels and get stable optical coupling for wide range of temperature. Bigger lens diameter can make better quality beam and smaller spot size at fiber facet. Then we could get longer transmission with OM3 fiber by lowering the model dispersion. Single-lab VCSEL could expect a longer lifetime than array, which will extend optical module lifetime and save maintenance cost in data center operation. We invented and developed first-in-class patented model coupling algorithm and integrated plastic injection mold optics based on fully passive alignment without any high-precision assembly machine. Single-head optical device is mounted individually at the optimum position to maximize optical coupling for all channels. Reference hole is working as the key to make optical alignment between optical device and fiber facet. The modular coupling has enabled highly scalable ramp-up volume manufacturing in a short term to catch up dynamic demand in SR product market. Individual VCSEL and PD die is mounted on the PCB at the pre-aligned position using commercial die bonding machine. Plastic mold optomechanical part is attached to the aligned PCB to get optical coupling between VCSEL and lens. Customized ribbon fiber is inserted into OSA by translation with a simple mechanics. Coupled optical power is monitored using GUI, and fibers are fixed to finalize the assembly. Direct fiber plug-in optical coupling can be used for all types of optical module, including AOC, cable-attached transceiver, and conventional transceiver in QSFP and QSFP-DD form factor. Minimizing the number of optical interface between fibers improves optical signal integrity. QSFP2 for SFP breakout AOC is popular to connect between switch to servers in the rack. Conventional breakout AOC includes a fan-out junction which is a big burden for cable management with a high port density connection. Our cable assembly does not require fan-out junction to make a breakout AOC, which is suitable for a top-of-rack application with a high port density switch and server. We measured optical eye for 400G QSFP56DD SR8 with OpenEye MSA mask specification. As you see the picture, there is no mask failure and its eye has a well-balanced shape for height and timing window at all PAM4 signals. BR for 400G SR8 at PRBS 31 was measured for OM3 100-meter loopback mode at normal operating condition with an MCB. The result shows error-free for 3 channels and maximum BR is 10 to the power of -11. We also measured the symbol errors per FEC block with the same sample with a 100-meter loopback cable. The maximum symbol error count is 2 for 2 channels only. All other channels have just the symbol error count 1. Our 400G SR8 transceivers can reach up to 150 meters using OM3 multimode fiber at 70 degrees C without problem. The maximum BR shows still 10 to the power of -9 and average BR maintains 10 to the power of -10 or lower. Our new optics design enabled the progress at high temperature and the longer length of the fiber without significant degradation of signal integrity. We tested our SR modules with a commercial 400G switch to validate real working environment. The samples are put inside the chamber together with the switch as shown in the slide. We chose the ports at the edge of the switch, which has the longest electrical length of interface from the switch chipset. No error of uncorrected code words with temperature cycling found at endurance test over 17 hours. We succeeded to get an excellent result with the commercial DSP version SR8 module in interoperability. We measured actual power consumption and BER of 400G AOC with the Keysight 400G tester to compare between analog CDR and DSP under the same operating condition. The cable lengths of AOC for analog CDR and DSP were 100 meter and 10 meter respectively. The result showed 21% low power consumption and the better BR of 1 or more order of magnitude with analog CDR 400G AOC relative to DSP AOC. We tried link testing of 400G QSFP DD AOC with a commercial 400G switch. We obtained a link up for all 32 ports without any problem. The maximum pre-FEC BR for the worst channel was in 10 to the power of -9 range. There was no FEC uncorrected code word for all 32 ports. We tested several interoperability items with commercial switches and NIC cards to confirm the compatibility of 400G module. We tried 400G and 200G AOC to multiple switches and NIC cards in the list. There is no issue found from the testing. We tried to connect the polymer waveguide array with our optical engine for a feasibility study on onboard optics with a parallel optical link. We modified fiber guide section of OSA to attach polymer waveguide array directly. It was joint work with Nitodenko, and polymer waveguide was designed and developed from them. The core shape is a square and it has a step index profile. We implemented a working sample with a QSFP56 form factor. The QSFP56 module was implemented and its optical eye was measured at case temperature 40 degrees C and 70 degrees C, respectively. The eye pattern shows good shape at 70 degrees C. The BR and symbol error count was measured for various case temperature from 40 degrees C to 90 degrees C to verify the durability of polymer waveguide at high temperature. The result shows excellent at 90 degrees C with a maximum BR of 10 to the power of -9th range and maximum symbol error count 2. Current work was initial demonstration result, and the design parameters were not optimized yet. 200G QSFP and 400G QSFP-DD products are in production for both AOC and SR transceivers. SFP and DSFP AOC is ready for pilot production. Any combination of breakout AOC is available. Our breakout AOC does not include ugly fan-out junction. We have best-in-class PAM4 AOC solutions as a flagship product, including QSFP-DD, QSFP, SFP, and their breakouts with a flexible combination of each form factor. We are doing the same with 25 Gbps energy products for both AOC and transceivers. Our transceiver can reach longer than standard SR specification with OM3 fiber, and cable-attached transceivers are attractive to highly dense and complex routing of end-of-row or width-of-row application with a patch panel deployment. I would like to summarize our approach and current status in PAM4 SR module and AOC. We designed and implemented SR module and AOC to meet all standard specifications. The following are the key features of our optics design. Our new optical engine has demonstrated an excellent SRA transceiver performance in PAM4 50 Gbps per channel as a result. Optomind is ready to support HPC and hyperscale data center applications with its PAM4 AOC and transceivers. The products are deliverable to customers now. If you have any question or inquiry, please contact me anytime. Thank you for your attention.
Thank you to both of our speakers. Those are really great presentations. First, to our audience, your questions are welcome. So please use the Q&A function and type your question in there, and we will answer as many as we can in the remaining 15 minutes of the webinar. So to start this off, I'd like to ask both of the participants. You didn't mention any activity with COBO, with onboard optics. How does that come in? And what are you thinking about that?
I can start this off. So co-packaged optics obviously is really an important development, and that's kind of COBO's mandate. And the idea is really to bring the optics as close as possible to the switch ASICs, to reduce power, to reduce cost and increase reach and so on. But also the challenge with that is, of course, it comes with technology risks to be able to develop that kind of technology. So what we're seeing right now is that the industry is used to a pluggable ecosystem, with DAC cables, with AOCs, SR optics, and transceivers, and we'll try to squeeze out as much as possible with those technologies. And for instance, the 800G evolution is really going to be predominantly based on these kind of pluggables. And then, of course, there are some standards that are trying to go beyond 800G, like for instance OSFP XD. But of course, to be able to reduce the power and increase the density to beyond 50 terabits per second switches, that is going to be a challenge. And I believe that co-packaged optics, like what Kobo is advertising, is going to play a critical role there. And what you see in the industry is now that instead of going straight to co-packaged optics, there's also kind of a near-packaged optics definition that is, makes it a little bit easier transition to go there, with a more relaxed channel definition in XSR plus, which should make it a little bit easier to transition to that technology. So it's going to happen. We don't know exactly when, and we don't know exactly what it's going to look like, but it's definitely on the roadmap.
Okay, Young-san, any comments on onboard optics?
Well, as of now, onboard optics could be migrate to near packaged optics. It is proposed last OIF meeting, and it's a hybrid solution between onboard optics and co-packaged optics. On that perspective, big cell optical interconnect could be a viable solution as of now, because big cell could be the best light source on the current commercially available for the optical interconnect, especially in data center solution, I think. So the co-packaged optics initially proposed based on single mode fiber only with some external high power laser source. At the end, it could be the right choice, but in the meantime, the near packaged optics could be a viable solution to develop and adapt at a real market situation, I think. Thank you.
Okay. So Young-san, a couple of questions about your presentation. So first, I don't know if you can go back and show slide 5. It's where you're talking about the benefits of VCSEL short reach optics and comparing AOC and saying that they can replace DAC over the 10 to 30 meter length. So I'm wondering, what is the cost comparison? Is there a strong economic case that you're saying there? Is it cheaper?
Well, I think it requires apple-to-apple comparison, but in reality, at the current market, DAC is well over widespread over the world. So the volume-wise, it's already the pricing and the manufacturing cost is already oversaturated. But on the other hand, AOC is a kind of some emerging stage in volume production. It could be similar to optical transceiver, but once we increase to volume, not just the same as DAC, but in the range of DAC within very short reach, if the case, we can reduce the significant cost, especially for the semiconductors, including chipset and big cell MPDs, if the case, and also the higher data rate, like 112 gigabps per channel case, DAC is not that cheap anymore. That's because they needed to select much better copper cable in material, and also they needed to tune, and also their production yield could be much lower than before. So I'm not sure the details of their productivity and cost in details, but I believe from 50 gigabps per channel PAM4 and beyond, we could challenge the DAC, or we may challenge active electrical copper first. Yeah.
Okay. Okay. Some questions from the audience. Young-san, what was the EMB of the OM3 fiber used in slide 15 and 16? With the transmitters underfilling the fiber?
I do not remember the number, and then I can answer or later to directly over through Jim. Yeah.
Yeah. Could you still show those slides? Slide 15, maybe.
His question is the underfilling the fiber. Yes, that's correct. Not overfilled launching.
Okay. So here you're showing 100 meters, right?
Yes, correct.
And at the end of your presentation in the summary, I think you talked about 150 meters.
Yes. We got this, even 150 meter with OM3. We got this. Thanks to the modal dispersion in the fiber, then we can achieve this kind of some abnormal result with OM3 up to 150 meter long. But this result is not a standard product spec. It's to showing our technology in the lab.
Okay.
Yeah.
Okay. Another question is about the market segment for the OSFP56 modules.
Well, we are targeting at the moment is the kind of some top of rack or rack to rack type of solution, and also straight 400G and straight 200G, especially for the HPC application based on InfiniBand interface. 200G straight AOC is the right choice, and it becomes more popular than ever these days. We are selling a significant number of that AOC, and multiple customers are attract that product solution these days.
Okay. Another question is concerning power consumption. And if I remember correctly, if you could maybe go to slide 19.
Oh, our 400G is the, when we measured with the Keysight tester, actual average power consumption was 8.3 watt per port, and the DSP one is over 10 watt.
So this is actually one of the maybe the key findings in your presentation, a key slide, right? At least that 21% power reduction. And that's going to be per link in your data center, and that adds up to quite a lot of energy.
Yes, correct.
So I suppose this is maybe the strength of the argument that this is where your cost savings are going to come from long term.
Well, as far as I know, the current SR DSP SR solution is using the same for the long haul application DSP chipset, which consumes much more power than SR solution. And recently, multiple DSP chipset maker is developing SR focused only, if the case that the power consumption will be reduced. Yeah.
Okay. So we have only a few minutes left in our presentation, but we're in our webcast. But of course, we welcome more questions to come in. In these final minutes, let's turn to 800 gig then. And I'd like to ask Kees if you could talk about what kind of testing has been done? I know that you had a slide there on the challenges at 112 gigabits per lane, and the need to develop test solutions and test tools for it. How would you characterize the industry at this point?
Well, that's a great question. Obviously, we're in an early phase, and we as an industry are figuring things out together. A couple of trends that I can mention is one is for instance, for system testing, which is really critical. Before you deploy your system, you want to fully populate your signal with transceivers, but obviously that's cost prohibitive. So you typically use loopbacks that are emulating the exact pluggables that you're going to use in your system. And at 400G, that was a very critical test, and you could use typical passive loopbacks to do that kind of test. For 800G, with the challenges that you see with signal integrity at 112G per channel, that is just not going to work. I mean, for the ideal channels, yes, but for the worst case ports, not. So we are now developing with some of the key players active loopbacks, where you basically recover the signal and retransmit it so that you can test worst case channels, and you can also test very complex pluggables that have some kind of link optimization included. So that's on one side. On the other side, for instance, for the active cables, so right now we don't really know exactly what is going to be the figure of merit. Eventually, of course, it's going to be the BER, but before that, how can you get to this optimum BER? What is the figure of merit that needs to be optimized? So you can look at S parameters, you can look at I diagrams to get to this optimum signal integrity, and then based on that, optimize the transmit receive equalization of the host ports, and also the equalization inside the active cable to get to that performance point. But that's really under development. We don't know exactly where it is going to go. Actually, we have a live demo of this at CIOE starting tomorrow, but we're working with the key players to come up with solutions so that those technologies can be brought to market. But it's different than 400G, and it's a little bit more challenging. So we all need to work together to develop these new procedures.
Yeah, so you mentioned, you showed a couple of slides with work at the OpenEye MSA, and has their work to date really been on for 400 gig modules, right?
Yeah, so OpenEye right now, that's a great question. So OpenEye right now is really at 50G per channel, and that's a characterization that we've done. So we're doing now a big interop event where we're testing, optical modules, we're testing links, we're doing the transmitter characterization. I want to make sure that all the, the data. The key is really that if you want to have a test parameter, an optical transmitter test parameter, it needs to have predictive value, what it's going to do in a link. So we're getting all the data, for the current generation. And this year, we're also going to start to look at the 100G per wavelength per channel implementation. And the key is really, first get the data. Once we have the data, we know it's going to work. And then you can have the final specifications as well as the test procedures. For OpenEye, it's analog, so we want to go back to kind of more intuitive characterization tools such as I diagram, and hopefully that's going to work because a lot of people are very comfortable to work with that, and it will just optimize the test procedures.
And as far as the maturity of the market overall, I suppose this begins with the module manufacturers, the cable manufacturers, then finally to the pluggables, the switches, and then the data center operators.
Yeah, that's correct. That's the ecosystem that we're seeing right now.
Yeah. All right. Well, excellent. I think we've reached the end of the hour, so I want to thank both of our guests for their participation here today. And also our thanks to the sponsor, DuPont Silicon Valley Technology Center and the Consortium for Onboard Optics. We will make this presentation available online for anyone. And with that, let's wrap it up and say goodbye. Thank you everyone for joining us here today.